expressing a matrix as the sum of symmetric and skew-symmetric matrices. Hello everyone. Today we are going to learn how to express a square matrix as the sum of a symmetric and a skew-symmetric matrix. Starting with our first slide, let's set the stage. In our previous lessons, we established a fundamental concept that any square matrix, which is simply a matrix with an equal number of rows and columns, can be decomposed or broken down into two distinct parts, a symmetric part and a skew-symmetric part. Now, you might ask why this is important. This process is mathematically significant because it allows us to take a complex matrix and analyze it more effectively. By breaking it down into two separate matrices, we can leverage their very specific and predictable properties to simplify our calculations and understanding. Over the next few slides, I will guide you through the conceptual overview, the exact formulas we use, and a step-by-step procedure to perform this decomposition yourself. Conceptual overview. For any square matrix, which we will call matrix B, we can express it as the sum of two distinct matrices, P and Q in simple terms, B equals P plus Q. To understand this, we need to define what P and Q are. First, P is a symmetric matrix. As we have learned previously, a matrix is symmetric if it remains unchanged when transposed. Therefore, P prime equals P second, Q is a skew-symmetric matrix. A skew-symmetric matrix is one where the transpose results in the negative of the original matrix. In other words, Q prime equals negative Q. You might be wondering how we can mathematically guarantee that any matrix can be split this way. The foundation for this decomposition lies in a specific mathematical identity. We can rewrite matrix B as 1/2 of the quantity B plus B prime, added to 1/2 of the quantity B minus B prime. To connect this back to our first equation, the first term, 1/2 of B plus B prime, represents the symmetric part, P. Similarly, the second term, 1/2 of B minus B prime, represents the skew-symmetric part, Q. Now that we have introduced the concept of decomposition, let's dive into the conceptual overview of how this actually works. Now that we have established the theoretical framework, let's move forward to the next slide, where I will guide you through the precise step-by-step procedure to perform these calculations. Step-by-step procedural guide. Now that we have established the conceptual foundation and the identity behind this decomposition, let us walk through the actual procedural steps. To express a given square matrix, which we will call matrix B, as the sum of a symmetric matrix P and a skew-symmetric matrix Q, please follow these precise steps. Step 1 is to find the transpose. You will need to calculate the transpose of the given matrix B, which is denoted as B transpose. As a reminder, this is achieved by simply interchanging the rows and columns of matrix B. Once you have the transpose, move to step 2, calculating the symmetric part, denoted as P. To do this, first find the sum of the original matrix B and its transpose, B transpose. Then, multiply the resulting matrix by the scalar 1/2. Mathematically, this is expressed as P equals 1/2 times the quantity B plus B transpose. Step 3 is to calculate the skew-symmetric part, denoted as Q. This process is very similar to the previous step, but instead of addition, you will find the difference between the original matrix B and its transpose, B transpose. Again, multiply the resulting matrix by the scalar 1/2. In other words, Q equals 1/2 times the quantity B minus B transpose. Finally, step 4 is verification. Because matrix addition and subtraction can be prone to small errors, it is essential to perform the following checks to ensure your calculations are accurate. First, verify that the sum of matrix P and matrix Q equals the original matrix B second. Confirm the symmetry of P by checking if the transpose of P is equal to P and third. Confirm the skew-symmetry of Q by checking if the transpose of Q is equal to negative Q. Once you are comfortable with these steps, we will apply them to a concrete example in the next slide. Illustrative example. We are given a square matrix, which we will call matrix B. This matrix consists of the first row, 2 and 4, and the second row, 3 and 1. Our objective is to express this matrix as the sum of a symmetric matrix, P, and a skew-symmetric matrix, Q. Let us begin with step 1, finding the transpose. As we discussed in our guide, we find the transpose, denoted as B', by interchanging the rows and columns. Therefore, the first row of B becomes the first column of B', and the second row becomes the second column. This gives us B' as a matrix with the first row 2 and 3 and the second row 4 and 1. Moving to step 2, we calculate the symmetric part, P according to our formula. P equals 1/2 multiplied by the sum of matrix B and its transpose, B'. First, let us perform the addition. Adding the corresponding elements, we get 2 plus 2, 4 plus 3, 3 plus 4, and 1 plus 1. This results in a matrix with the first row 4 and 7, and the second row 7 and 2. Now, we multiply this resulting matrix by the scalar 1/2. This gives us matrix P, with the first row 2 and 3.5, and the second row 3.5 and 1. Now, let us proceed to step 3 to find the skew-symmetric part. Q. The formula here is 1/2 multiplied by the difference between matrix B and B'. First, we perform the subtraction. 2 minus 2, 4 minus 3, 3 minus 4, and 1 minus 1. This gives us a matrix with the first row 0 and 1, and the second row -1 and 0. Next, we multiply this by 1/2, resulting in matrix Q, which has the first row 0 and 0.5, and the second row -0.5 and 0. Finally, we reach step 4, verification. It is crucial to verify our work to ensure accuracy. First, let us check the summation. If we add matrix P and matrix Q together, adding 2 plus 0, 3.5 plus 0.5, 3.5 minus 0.5, and 1 plus 0, we arrive exactly at our original matrix B, with the first row 2 and 4 and the second row 3 and 1. Next, we verify the symmetry of P. If we take the transpose of P, we see that the matrix remains unchanged, confirming that P is indeed symmetric. Lastly, we check the skew-symmetry of Q. The transpose of Q results in a matrix with the first row 0 and -0.5, and the second row 0.5 and 0. This is exactly the negative of matrix Q, which confirms that Q is skew-symmetric. With these checks complete, the decomposition is fully verified. Now that we have established the theoretical foundation and the procedural steps in the previous slides, let us apply them to a concrete example to see how this works in practice. In the next section, we will explore a real-world analogy to understand the intuition behind this process and discuss some common mistakes to avoid during your calculations. Real-world analogy, data balancing. Now that we have walked through the theoretical steps and a concrete numerical example, you might be wondering why we bother splitting a matrix in this way. To help you visualize the purpose of this process, let's look at a real-world analogy involving data balancing. Imagine you are analyzing a network of 2 cities. In this scenario, let's say the original matrix B represents the flow of traffic between these 2 locations. Recall that we decomposed matrix B into 2 distinct parts. The symmetric part, which we labeled as matrix P, represents the balanced or mutual flow. You can think of this as the average volume of traffic moving in both directions. Conversely, the skew-symmetric part, which we labeled as matrix Q, represents the net flow or the imbalance. This part of the matrix specifically captures the difference in traffic direction, essentially showing us the bias of flow from one city to another. Therefore, by splitting the original matrix, you can effectively separate the general volume of traffic from the directional bias. This allows us to analyze the stable part of the data separately from the shifting part. Now, while the concept is intuitive, the actual calculation requires precision. In the next slide, we will discuss some common mistakes to avoid so that you can ensure your results are always accurate. Common mistakes to avoid. Now that we have walked through the procedural steps and seen a practical example, it is important to discuss some common pitfalls. Let's look at the most frequent mistakes students make during this process so you can avoid them. First, be very careful not to omit the scalar 1/2. A very common error is to calculate the sum of B and B transpose, or the difference between them, but then forget to multiply the resulting matrix by 1/2. If you miss this step, your final verification will fail because the sum of P and Q will equal 2 times B, rather than the original matrix B. Second, pay close attention to sign errors during subtraction. When you are calculating B minus B transpose to find the skew-symmetric part, be meticulous with your negative signs. Keep in mind that the element in the ITH row and JTH column minus the element in the JTH row and ITH column must result in the exact negative of the element in the JTH row and ITH column minus the element in the ITH row and JTH column. Third, here is a helpful sanity check for your work. Always examine the diagonal elements of your skew-symmetric matrix. Q, by definition, these diagonal elements must be 0. If you see any value other than 0 on the diagonal of Q, you can be certain that a calculation error occurred during the subtraction of B and B transpose. Finally, ensure that you do not confuse the transpose of a matrix with its negative. In all our formulas, we are using B transpose, which involves interchanging the rows and columns. Do not mistake this for negative B, which would involve changing the sign of every element in the matrix. By keeping these 4 points in mind, you can ensure your decompositions are accurate. Now, let's move to the final slide to summarize our key takeaways. Key takeaways. First, the fundamental principle we've covered is that any square matrix B can be uniquely expressed as the sum of 2 specific matrices, P and Q. As we detailed in our procedural guide and worked through in the example, the symmetric part, P, is calculated as 1/2 of the sum of matrix B and its transpose, B prime. Similarly, the skew-symmetric part, Q, is determined by taking 1/2 of the difference between matrix B and its transpose, B prime. A critical point to remember, which we highlighted when discussing common \text mistakes, is that the diagonal elements of the skew-symmetric matrix Q must always be 0. If you see any other value on the diagonal of Q, it is a clear sign to recheck your subtraction. Finally, always remember that verification is the most reliable way to ensure your calculations are correct. Once you have found both parts, adding P and Q together must return you exactly to your original matrix B. To wrap up our lesson, let's review the key takeaways to ensure you have a solid grasp of this decomposition process. Keep these points in mind, and you will be able to decompose any square matrix with confidence.